All right, so wait, hold on, still starting. All right, so this is our final presentation for this semester. We're going to talk through everything we did, starting with the first document we did, the teamwork contract, moving into the project proposal, the design phase 1 document, and the design phase 2 document. And the way we're going to present this to you is we're going to talk about everything as if those were the decisions that we had stuck with right now. But then as the presentation progresses, we're going to show you how things have changed and where we're at right now. So the first document that we produced this semester was the teamwork contract, and it was designed to help us lay out our expectations for how we would work together through the semester. And we stated explicitly that we expect full participation from each member so we could avoid problems later in the semester. And we're all friends. I'm married to one of our members, so we really did not have very many problems this semester. We decided on some roles for a few of our members. I'm the team leader. Katie's our security officer. Jason is our hardware specialist / CAD specialist. And Maddie is our communications coordinator.
So the next thing that we did was our project proposal. The goal of this project proposal was to provide evidence that our project was worth the time and resources we were going to spend on it, and that we were the right group to take it on. Our goal overall is to use our electrical and computer engineering backgrounds to solve a problem that we observe in the restaurant industry.
So our problem statement, which we went in depth in the project proposal, basically is to address the problem of waiters and waitresses who are feeling overwhelmed, and also just like wanting to not only make their life easier, but also help companies be able to have their servers be more efficient and thus save money and then have happier customers. And so that is the problem we were trying to address.
And our proposed solution to this problem is a smart coaster system, so that when a drink gets low, then the waiter will receive a notification, and they'll know that they have a table to assist. With this, we have also added some additional features to try and help make lives easier on both sides of the coaster, and that includes an assistance and do not disturb notifications, self-organization between the coasters and tables, an app that makes all of the information easier to access, and a charging station for the coasters. So for our background, we are going to, in this section, talk about our engineering and STEM topics that are relevant to what we have encountered over the course of our project. So the first thing is with the mass measurement. We're looking at different ways of measuring the mass of whatever's on top of the coaster. And what we came down to is a strain gauge system. And so we were looking at load cells that include strain gauges. And essentially, the strain gauge would act as a variable resistor with 2 points to measure the voltage. The most common organization is a whetstone bridge, and that is a quarter bridge configuration of the whetstone bridge, which has one strain gauge with 3 resistors in combination, and that forms a quarter bridge whetstone bridge, and that will help measure the voltage difference. That voltage difference can then be amplified and turned into a readable signal that can correspond to weight measurement.
So next, we talked about 3D printing, because that's a pretty big part of our project. We're going to be 3D printing the coaster case and the docking station. And we found out that some 3D printing filaments can actually be pretty toxic, so we wanted to avoid those. Some of the most popular types of 3D printing are the fused deposition modeling, but the types that the Tennessee Tech University has and the ones that we will be using our material extrusion brace 3D printers, and continuous fiber reinforced 3D printing.
So for the self-organization aspect of our project, we settled on radio frequency identification. Our plan was to use passive tags inside of the coaster and readers on the table that would read the tag inside of the coaster and send the coaster's ID to a database where the location could be stored. The reason we chose RFID is because it had a better range, or a higher fidelity resolution than the other options for RTLS systems. And we thought it would also be cheaper than other RTLS systems. And yeah, that's pretty much why we were at RFID at the time.
So for the communication, we obviously needed a way for the coasters to communicate with the app and send the notifications and their status and their location. So originally, we were looking at using the Zigbee protocol on an XB chip, which is like a networking shield that you can attach to Arduinos and Raspberry Pis and other things. So this Zigbee operates on the 2.4 gigahertz standard, and originally it was so appealing because it had a mesh topology and had low power consumption, and so and it was like, not proprietary, so it was a little bit on the cheaper side. And so for that, our plan was to use Zigbee over an XB chip, but we also were thinking an XB chip because it allows you to also use Wi-Fi or a couple other internet protocols in case Zigbee didn't work out.
So with all of the background information in mind, we came up with a list of specifications that we wanted our project to accomplish. Our system has many subsystems within it, and we wanted at this point to come up with what we needed each system to do. So we, first of all, wanted the coaster to relay information if the drink on top of it was low. We were thinking already at this point that it would work on a different system, so whatever it is initialized at, we work off of a difference between the initial weight and where it's at, and once that difference reaches a certain threshold, that would trigger a notification. In addition, we also at this point wanted to implement an assistance button so that we could have the patron call for help without looking around the restaurant and trying to wave down a waiter. They can just simply press a button on the coaster and a notification would be sent to the server. With the assistance button, we also came up with the do not disturb idea. Restaurants are a prevalent setting for business meetings and other important family conversations. So we wanted to be sure that if we're implementing a smart system, that we give the patron an opportunity to simply flick a switch and then not be bothered, so that they can carry on with that important business meeting or that important family discussion and not be bothered by the server. Also, just stemming off of the idea of trying to make this as smart and self-sustaining as possible, we wanted to implement self-organization. At this point, as Josh mentioned, we were looking at RFID, and we were actually looking to make that a system so that every seat had an identity, and that coaster, and that each coaster would also identify, and then a reader underneath the table would pick up on the passive tags and choose which one it needed to. Other specifications is that we wanted the battery management to be overall successful. What we defined as successful was we want the battery to last all day, and we wanted it to be able to charge overnight to 100%. We also need the coaster itself to be waterproof because there are so many electronic systems. And the idea at this point was also to have an app that would be given that an iPad would be given with an app loaded onto it for all of the servers to help increase their time. So these were the general specifications at this point, and we've more or less stayed with them, although there have been changes on how we've done that.
So for the constraints, we came up with a few things. We looked up some stats on the average size of tables inside of restaurants and found that they were around 300 square inches. We found that the average eating area for a customer was around 300 square inches. And we decided that we wanted to take up less than 10% of that space. So we constrained our coaster size to a maximum of 30 square inches, which means if it was to be a square, it would have an approximate length of around 5.5 inches. A couple other constraints we put in place were IP rating. We wanted the coaster to have an IP rating of 44, which means that the device would be protected against water splashes from any angle and from solid objects greater than 1 millimeter in size. We didn't think that it needed to be designed so that it was capable of surviving being completely submerged in water, but at least it needed to be protected from splashes and food particles. Another constraint that we put in place was we only wanted to send the state of the coaster to the database if the coaster state had changed. And the reason we wanted to do that was to save electrical power and processing power. Yeah. So then for measures of success, this section goes over how the team will determine if the project is successful and how we plan on testing those measures. So one example was the IP rating discussed in the constraints section. So for the IP rating, we planned on taking the coasters, or a coaster that we had made, and splashing it with little parts of water without the components inside, of course, and testing to see how much water got inside of the case. And we also were going to throw little crumbs at it and put it in maybe a bag of crumbs and see if anything was able to get inside. So, and then another measure of success was we wanted self-organization to work. And we believe that a successful project would have self-organization at a seat level.
So throughout the project proposal stage, we also wanted to look at all the different solutions that were available to make sure that we were either learning what we could or also making something that was unique in its own way. And so first we looked at just the different tabletop devices that many restaurants have implemented. So this includes like Ziosk and Presto and a couple others that allow you to pay at the table or play games, because that was something that's been produced in a restaurant setting that is somewhat similar to our concept. And then also, along with that quote talking about how this tabletop technology improves average sales and increases productivity. And so a couple other, here, Josh, could you mute? Sorry. A couple other different solutions that we came across were a couple of, different people that did a single coaster that measured like the weight of a glass or sent a notification to an app like to drink water. And so there are some different kind of, project-y solutions available for that. But many of them, I think all that we saw were only a single coaster and not several coasters working in unison and communicating with each other. And secondly, there were not any that were self-organizing like we have defined it to be, as in knowing where they are, being able to communicate where they are with each other and with an app, And so we really feel like that kind of set our project apart from those, and just being able to have multiple coasters to be used in a restaurant setting. So those were some of the different solutions that we came across while researching for this project.
So in analyzing our concept at this point of our project, there were some risks that we needed to address. The first risk it includes batteries. Batteries we found are incredibly inconsistent. So finding one that will hold the necessary charge quickly enough, fit inside the coaster, those are all issues with finding the correct battery for us. The system is low power, and so that does reduce the risk because it reduces how much charge we need the battery to actually hold, but it's still a critical component. Time at this point was also known to be a risk because as a group we acknowledged that this was not an easy project and there are plenty of skill gaps that we are having to take time to solve. One other risk is the mass measurement system. It is critical to our project and it is not an easy task because there are so many different variables, different classes, different liquids, different amounts of ice. So creating a perfect solution to this will be difficult, and there are a lot of variables that come into play, making that part very risky. Any other risks include the budget, which our project is fairly low budget, so we don't think that we think that it is fairly affordable, and there's not much physical harm to be done with this project. So, yeah.
Okay, so some of the resources that we wanted to go over were that we needed a 3D printed coaster body, a weight sensor, a battery, a processor, and a communication chip. These were all components that we were going to need to complete our project. So some of the other things that we consider resources are the skills that we had to learn. We needed to go over AutoCAD, battery management, PCB design, app coding, and networking. And then we also have a timeline that we laid out. So at this time, our timeline was pretty vague. We didn't know exactly what tasks we were going to need to accomplish. So it just includes the broad things that we needed to get done this semester. And the things for this semester was just the design phase 1 and the design phase 2, which we have mostly successfully done at this point.
So then we got into broader impacts, and this section really just touched on how our project might impact the economy, the world, if it was to actually be made by a real engineering company. So first thing we touched on a move towards fully automated restaurants as replacement for human workers, and we basically explained why we don't want that to happen and how our project is not a precursor to something like that. And then we also touched on the 3D printing and how dangerous chemicals can be emitted through 3D printing. So if they were to be mass produced in a factory, we would want to use some of the safer, non-hazardous ways of printing the coasters. And yeah. So moving on to design phase 1, this document goes over some of the systems and subsystems inside of our project along with their specifications. So the biggest subsystem of our project by far is the coaster. And the main task of the coaster is to determine the state of itself at all times and send the information about its state to the hub. The state includes the location of the coaster, whether or not the drink on it needs a refill, and the status of the assistance and do not disturb buttons. And each of those states are measured by a different subsystem within the coaster that we are about to get into. So first, the microcontroller. The microcontroller is the central component of the coaster. And we decided that an Arduino would be the best option for the microcontroller, just because we have a lot of experience using Arduinos, and it should be pretty easy to connect a bunch of different sensors up to the microcontroller. So it'll be connected to the strain gauge for weight measurement, a XP chip for, at this point we were thinking it was going to be connected to an XP chip for networking capabilities, and to an RFID module, whether that was an active tag or a reader, we weren't entirely certain on at that point.
So the microcontroller connects to the strain gauge. The strain gauge is on a load cell, and we have at this point chosen a bar load cell. And so the strain gauge in combination with the other resistors that the load cell contains will transfer a signal to the microcontroller. When a weight is placed on the coaster, the bar, which will be connected to the bottom of the coaster and the top of the coaster, the bar will bend slightly with the pressure of the weight, and this pressure will add extra resistance to the gauge, which will change the output voltage, which we can then measure an exact mass off of that voltage change.
So for the network chip, like I mentioned earlier, we were planning on having a XP chip that we would basically either plug in or solder to our microcontroller. And so the idea was to have a XP chip in each of the coasters, and then one in the hub, which we'll talk about in a minute. That way we could send the data wirelessly through Zigbee. So a couple of reasons that we were considering this is because XP has a low power consumption, which is ideal for, especially since the coasters are battery powered, is ideal for our project. And then another reason that we were looking at doing an XP chip is, like I mentioned, it can host many different protocols and has several different like mesh topology and several different specifications that fit our use case. We were also considering doing Wi-Fi just because it is another popular internet protocol instead of Zigbee. But we were, in going back and forth, Zigbee tends to use only in like, I think, the microwatts of power consumption, while Wi-Fi was or maybe it was tens of microwatts for Zigbee, and then more like 100 microwatts for Wi-Fi. And so we were thinking if those are, basically have the same, specifications for everything else, why not pick the one that's slightly more power conscious? And so that was why we chose XP at this point in the phase 1 design.
So the next thing we're going to go over is the assistance and do not disturb button. These will be on the side of the coasters, and they will be a button for assistance and a switch for do not disturb, and they will have LEDs associated with each of them as status lights. So when these buttons are pressed or the switch flipped, they will send a signal to the microcontroller, and the microcontroller will adjust the LED appropriately and send a message through Zigbee into the app through the hub. So then the app will receive a notification and adjust the status of the table for the waiter to see that. And then so we talked about testing that. We could set that up on a breadboard with just LEDs, resistors, and an Arduino, and make sure that that works the way we think it should. And then next is our battery. So the battery will power the microcontroller and has to be rechargeable. To test different batteries, the team will perform research on different candidates to determine their battery life and size. So the size is important and must be big enough to run the coaster for a full day. And that's the only important thing about it.
For the network hub, at design phase 1, we had decided that we wanted to consolidate all of the information from the coasters before we sent it to the application. So that way, we didn't want to try to connect coasters to individual iPads or anything like that, because it could get out of sync, or that would be very difficult as far as scalability and if we wanted to add more coasters. And so with that in mind, we decided to use a messaging protocol called MQTT. And so this is a publish subscribe messaging protocol. And so we were planning on hosting this on a Raspberry Pi, which is a system on a chip. And one of the reasons that we chose a Raspberry Pi was just because it is extremely well documented. It has a bunch of different form factors. And so, especially in design phase 1, where we hadn't nailed down exactly, what we're looking for as far as hardware goes, picking a Raspberry Pi that is very well known and has a lot of options was very appealing. And so, in addition to this, with MQTT, we planned on testing it by communicating with a Raspberry Pi and a computer, and then, testing it between a Raspberry Pi and a computer. One thing that I did a lot of research on and went back and forth a lot with was MQTT and what to use as a broker. And so up until a little while ago, I didn't know that you could even do a broker as like on the cloud instead of having a physical device. And so later we'll talk about kind of some of the pros and cons with that. But at this point in the project, we just ended up knowing that we wanted a Raspberry Pi to be our MQTT broker, and that way the coaster would publish messages to the broker and the app could subscribe to messages from the coasters.
So for our conceptual design for the self-organization section, we decided to implement an RFID reader underneath the table. And each of those RFID readers underneath each table would be responsible for determining the location of the coaster in the restaurant. If a coaster had been placed on the table, then the tag inside of the coaster would be read by the reader, and the reader would then send information about which coasters were on its table to the database. The reader model that we were looking at confirmed that it could read up to 200 tags per second, which was very desirable for us since we were looking at possibly having tables of parties of 8. And we were going to adjust the range on our RFID reader by swapping out different antennas to figure out what works best from seat to seat. And we determined that the reader and the tags should be tested in person because there was no simulation software available that could accurately determine the read radius of the reader and whether or not it would be able to read through the materials like the table. It's a good thing that we did not decide to test those in person because the readers are very expensive, but we'll get into that later. And then for the app, we decided to go with an iOS app, and we decided to code it in Swift using Apple's IDE Xcode. And the biggest reason we decided to go with an iOS app instead of an Android app is because iPads are much more widely available than Android tablets, and we feel that more companies would rather go with Apple over Android just because they're a more trusted company. And we decided to use Swift and Xcode because Apple designed those tools specifically for developing iOS devices. And at this point, we wanted to show like every table in the restaurant and every coaster and what waiter and waitress they were assigned to. And if this was to be an actual engineering project from a company, that it's something that we would definitely want to do. But at the moment, we're probably not going to have enough time to get to that.
So for the docking station, the docking station's purpose is to charge the coasters and also to house them overnight. So there will be contact points on the coaster, and they will easily align with the spots on the docking station where there's going to be power rails. So you just like stick your coaster in its little cubby hole and it will charge overnight. And so this was our resource and timeline that we made for design phase 1. So we actually listed out each task that we needed to complete and put it in order according to what we decided was needed to be prioritized. So things like learning how to do things were put ahead of actually doing them, because that's how things work. You need to know how to do it before you do it. And things like testing the weight thing was put before designing the coaster, because testing our weight component is a really critical part of our project, where designing the coaster can be pretty easily modified fairly quickly. So yeah, that was our Gantt chart for design phase 1.
So this is our ARA consideration little graphic. And so ARA stands for Architectural Risk Analysis. So basically just trying to identify possible cyber threats and ways that we can address them. So in the blue boxes, we have our attack surfaces. So this is where would be possible entries for people to attack the different pieces of our project. So we have the Bluetooth LE beacon, the coaster, the actual MQTT server or the broker, the app that we're building. And then if we end up implementing a database, that would be a pretty large attack surface, because that's where we would store all of the information from the coasters. And so then we also have our data flow, which are the blue arrows. And so this shows the different ways of us transmitting the data. So some of the different ways that we would transmit would be Bluetooth LE, Wi-Fi, and MQTT. And so for each of those, there are different vulnerabilities. And so some of the ways that we would try to mitigate those would be for Wi-Fi, we could put it on a separate guest network and then have a unique ID and password. So this would mean that, if we implemented it in a restaurant somewhere, we wouldn't have to really change their Wi-Fi at all. We would just add our own guest network. And then this would also make it more secure, just in that it's not the public restaurant Wi-Fi that everybody's using, but it would be our own dedicated Wi-Fi network. And then for MQTT, that messaging protocol actually offers end-to-end data encryption. And so for that, you can encrypt the message going out, encrypt the message coming in, just to make sure that there's no man in the middle or spoofing. And then for Bluetooth LE, one possible risk would be spoofing of the Bluetooth LE beacon. Right now, we think this is of pretty low likelihood and low risk. Although, if we deem it an important enough risk for the time ratio, we can also do a type of encryption, which is sending a digital signature with the beacon. And so this would just say that, okay, this is a valid beacon that the coaster is reading, and make sure that the coaster is not off on some island and we think it's, at table 6. So that's pretty much the layout for the ARA considerations. And then we also have our trust boundaries for the coaster and the database. And then we also, now with how we're doing Bluetooth LE, would have one around the beacon as well. And those are just kind of saying that, okay, once it leaves the beacon or once it leaves the coaster, we are now exposing ourselves to another layer of either vulnerability or just openness. And so that's kind of the description of our graphical. And then the threats are, showed in the little green spiky blobs.
All right, so for our ethical consideration section inside of the document, really the biggest thing that changed here from the project proposal is our use of RF technology. We found that there are stipulations set in place by the FCC that requires RFID readers of the specific power that we were planning on using in this project to be at least 21 centimeters away from people to protect them from long radiation exposure and interference. So that was something that we were pretty concerned about. And as an added bonus to that, there was also a possibility where they could interfere with implanted medical devices, such as pacemakers. So you'll see in the next section in Design Phase 2 that we moved away from RFID, and you kind of got a taste of that in the ARA section. And I just wanted to make a comment on the ARA section. That was for the project as it stood during Design Phase 2, but it was added to the Design Phase 1 document. So that's why it mentions BLE beacons inside of the ARA diagram. Just wanted to clarify.
So at this point, we have hit design phase 2. This is where we are going to give detailed design of each system, and this means we, from our design, we could actually take our artifacts and build them. So the biggest portion is the coaster. So we have taken the coaster system and divided it into 6 subsystems to help accomplish its goal. After this slide, we are going to dive into each of those subsystems and explain the choices that we made and why we made them.
So this is our circuit schematic for the microcontroller. And as you can see, it details all the connections that the microcontroller is going to have between all of the different subsystems and sensors inside of the project. The whetstone configuration shown down there in the bottom is the load cell, and it is connected to the HX711 module. Up there on the right, you can see the LEDs and the do not disturb switch and assistance button, and those will be implemented on the PCB. And then on the left, you'll see a change. That is the Arduino Nano 33, and that is a Bluetooth model that we will be using for self-organization instead of RFID for obvious reasons detailed inside the Design Phase 1 document. And also, there's a difference in the microcontroller choice, or rather, we've picked a specific microcontroller rather than just saying we were going to use an Arduino. The Arduino Uno Wi-Fi Rev 2 was chosen so we could upload directly to the MQTT database.
So for the load cell, we have chosen a 5 kilogram bar electrical strain gauge. So that will be inside of the coaster, and that will be responsible for measuring the weight placed on top of the coaster. As we will see later in the actual coaster design of the casing, it will be connected. The strain gauge will be connected to the top and bottom of the coaster, and it will be the only connection between the two. With that setup, it can accurately measure the weight placed on top without being interfered with other connections between the top and bottom of the casing. When we were going to choose our load cell, we did a test where we took an ordinary kitchen scale and measured a variety of glasses with variable liquid levels, and ice. This was to give us an idea of what category of strain gauge we needed, and what kind of weight measurement we needed it to be able to measure without getting overloaded. And so that is why we have settled on a 5 kilogram, because it should give us the accuracy and precision that we need with the lower levels of grams without being easily overloaded if we tried to cut it close with something like a 1 kilogram gauge. So that is why we have chosen the load cell that we have.
All right, so for self-organization now, we will be using a Bluetooth or BLE connection. We're going to be using BLE beacons on the table and a Bluetooth receiver chip inside of the coaster. And the way this is going to work is we're going to use RSSI, which stands for Received Signal Strength Indicator, to determine the location of the coaster. So the beacons will be constantly transmitting a message, and basically that message is just, hey, I'm here. And the coaster will be receiving that message and calculating the strength of each of the beacons in the room and comparing them to determine where it's at the room. And the reason that we chose to do Bluetooth over RFID is, one, Bluetooth is much cheaper than RFID. The RFID readers were going to run us around $200 per table, but the Bluetooth Nano chips will only run us around 20 per table. So 90% decrease there, which is great. And so we're actually planning on using an Arduino Nano as both the Bluetooth receiver and the Bluetooth beacon. And the reason for that is so we can test multiple beacon protocols to see which one might give us a more stable RSSI and which one might be better for determining indoor location. Yeah.
So here we can see a 3D view of the preliminary PCB design. In this design, what is shown is the front of the PCB, and there is another layer on the back that has more traces as well. So in this PCB, there are two switches. On the bottom right is the button switch, and that will be for the assistance button. And the switch on the bottom left is going to be a single pole double throw switch. So it will be basically a binary system, so that one of them's on, the other is off. And that will be how the switch works for the do not disturb switch. With both of those, they are connected so that wherever it would go to the microcontroller, there is a resistor, and it is going to be a 220 ohm resistor. And then these will all use digital pins, and on the top you can see the two LEDs. Those LEDs will also have resistors before they go to their respective digital pins as well.
So then for the battery, we have zeroed down just a little bit for the battery specs. So we know that Arduino runs on 5 volts, so we will be using a 4 AA battery pack, which gives us around 6 volts. And there will also be a battery management system in the coaster that monitors the battery, protecting it from input surges, over voltage, and over current. This will be connected to the voltage bars that are connected to the charging station during the night, so that it can also charge our batteries.
So here is the current casing design for the coaster itself. We've chosen a square design to make it easier to work with, and because a lot of other components come in square shapes, we thought it would be easier to fit, as well as make the docking station easier. On the right, you can see the base of the coaster, and this is the first part of it. There are threaded holes for screwing in the Arduino Uno and on top, and the Arduino Nano on the bottom. There's also an additional hole to the left of the Arduino Nano spot, and that is for the base connection of the strain gauge. And then the strain gauge will go out at a diagonal towards the center, so that where the coaster actually gets weight in the center is where the strain gauge will measure from. On the left, you can see the top part of the case. So the design here is that it should fit just around the base of the coaster. and basically slip on top of it without any actual connections besides the one of the strain gauge. So strain gauge will be the only real connection between the bottom and the top of the coaster. So that cylindrical thread in the middle of the top of the case is going to be the single connection. On the left are also the 4 holes, and those holes correspond to the 2 LEDs and the 2 switches. That will be the access point for the switches, so that the customer can have easy access. And the PCB is being made thin enough so that it can sit flush against the side wall, and they can stick directly outward. The components can stick outward.
So for the hub, a lot has changed between design phase 1 and design phase 2. So like I mentioned earlier, we were planning on using a XP chip and running, transferring the data through Zigbee internet protocol. However, some of the issues that we ran into were had to do with, one, interference. Zigbee is on the same channels as Wi-Fi and it is less powerful. So if they are both running at the same time within a certain range, Zigbee will just be overrided. And then another issue that we ran into it with is just size in the coaster. So to have the XP chip mounted on top of whatever Arduino we had would be just another size increase in the coaster. And so then having to have that somehow be compatible with what we were thinking we would use was RFID tags inside the coaster. So we decided to simplify it to just getting a Arduino that has Wi-Fi on board that we can post straight to MQTT and not have to use another protocol that has its own chip and everything. And so that simplified a lot for us. And then for the hub, I also did a lot of research and went back and forth about whether to have a cloud-based broker or a physical-based broker like we were originally considering. And so after a lot of research and, talking about the different security pros and cons to each one and costs of both of those, we decided to go with the physical broker on a Raspberry Pi, which would also allow our original idea of possibly extending it into a database where we can store and then look up trending for the different notifications. We decided to go with the physical broker. And so as it stands now for design phase 2, we've ordered a Raspberry Pi 4 with 4 gigabytes of RAM and 32 gigabyte micro SD card. And so that gives us all the power we'll need to host this MQTT broker, receive all the messages, allow the app to subscribe to it, and then also give us the possibility of having our own database.
So for the app in design phase 2, not much has changed except for that we're going to make it smaller because a lot of the team's focus has been shifted towards really making the self-organization work. So the GUI on the app is going to simply have the first, we're making 2 coasters for the project. So it's simply going to have coaster 1 and coaster 2, and it's going to display those states. It will be a really pretty GUI. We haven't designed the GUI yet, but I've been taking a course all semester on Swift programming and gotten some practice on a Mac that we've borrowed for the project as well. So the Bluetooth beacon I touched on earlier in the presentation a little bit, but the main thing with this is, well, first of all, we chose to use the Arduino Nano 33 IoT, but we wanted to show why that Nano meets our requirements. The first is that it can send out multiple beacon protocols, and we'd really like to test a few of those and see which one works the best. And then we also did an experiment to make sure that the Nano could do what we want it to do. So I found a similar Bluetooth chip inside of one of my printers that had similar specs, and placed it underneath the table. I placed the whole printer under a table, put it on a chair, and then I placed my phone on the table and measured the received signal strength indicator at various points on the table. So the 4 data points that I took, I checked 8 feet away, which would be off the table at another table. I checked at both edges of the table 3 feet away, and then I checked directly on top of the Bluetooth chip. And I had this app plot the RSSI for me, and then I found the statistics on the average received signal strength indicator for each of those measurements, and then I found the standard deviation. And concluded that the standard deviation did not fluctuate enough to create a problem with the receiver not understanding the signal strength from the beacon, and that there was a great enough difference between the data points that it should be able, for the most part, to tell which table it's at just by simply figuring out which signal strength is the largest. And if that doesn't work, we have a plan. We're planning on using a machine learning algorithm or a search tree, possibly, and taking a bunch of data points and running through the search tree to determine the location of the coaster. Yeah, that's why we chose the Arduino Nano, just so we can do some experiments.
And the last thing is the charging station. And the charging station design has not been updated, but the specifications are still the same. It needs to house all the coasters overnight and provide them with enough power to last a whole day. And the design is still the same for that, with just the charging rails, which will have contact points that touch to the coaster. So then for our timeline, we just want to talk about how our timeline progressed over the semester. The timeline introduced in the project proposal was followed to the best of our ability. The one in the project proposal was really vague, so it was pretty easy to follow. But then we pretty quickly after that made a really detailed Gantt chart that showed what we needed to get done in a timely manner so that we could get everything done in the semester. We did not always complete all of our tasks, but this was mostly because we changed what we wanted to do. So we talked about RFID a lot in our Gantt chart, but then we ended up going with Bluetooth, so we're not going to end up testing RFID, which is on our original Gantt chart. So yeah, that's our timeline.
So as far as what we all contributed to, we kind of laid out the basics of like what everyone focused on. So for Josh, he did a lot of research on self-organization, then taking the class for coding in Swift to make the app, and is also our team leader. So he's put in a lot of time in keeping everybody on track and organizing meetings and making sure that we're all on the same page and updated and know what we need to be working on. Maddie has done all of the work on the battery, I believe, and just doing our power management circuits and also working on the docking station and designing that. And in addition to that, she has been our PowerPoint guru. And so she's done a great job of pulling all of those together and making them look cohesive and making sure that we have the right information and making them look professional, and then informing each of us of what we're talking about and organizing presentations and handling a lot of that takes time and is sometimes can be difficult to like have motivation to do. So she's really taken that up. And then for myself, I've handled the networking and the hub management. So a lot of the internet protocol research and how we're going to have everything communicate and stay synchronized. And then I also talked about the ARA considerations and doing an analysis on that. And so trying to go through and then identify all the different like solutions and vulnerabilities there and how we can address those. And then just throughout the project, trying to be conscious of the different cyber vulnerabilities. And then Jason has been the head on the coaster design. So he's been doing all the work designing the layout for the coaster and how it's going to be put together, like in the software and just outside of that. He's also been in charge of PCB design. And so he's been taking, I think, the largest role in the hardware aspect of our project. And so he designed the PCB for the LEDs and the switches. And then he's also been the main person that's been doing all the work for the weight measurement system. And so there was a lot of research that went into that for the Wheatstone bridges. And so he's been our go-to as far as hardware goes and making everything fit together in the coaster. So we will actually have something at the end of our capstone. And so, yeah, we've also all helped out. Obviously, these are very interconnected. And so I do feel like everyone's done a good job of communication and talking about the different needs that each subsystem has and how those connect. And so that's kind of how we've all contributed this semester. And so I think that sums up pretty much our semester, but.
Yeah, that's pretty much our semester in a nutshell. So thanks for hearing us out. We've been great.